inside of the RosHub engineering team. One of the questions we were asking ourselves about ROS was, how might a person go about cloud scaling ROS 1.0? Because we started talking about RosHub back in 2014. So first off, let's take a quick step back for the newcomers in the room. What is ROS? ROS is basically this thing that gives you a ton of capabilities in robotics and a lot of features. Features like communications, generic robot APIs, and a common set of tools and tooling that allow you to visualize and see your data. So the big thing, when I first started in robotics, you had to build literally all of this stuff yourself. My first internet-connected robot was in 2002, and nothing like this existed. So, I mean, not even the programmers to flash the Atmegas that we were using these were things we were putting together by hand. So, as soon as I discovered ROS, I was like, holy crap. You know, the whole background of people who helped build ROS really came out of a couple of different corners, and I actually didn't, I really should have included Player Stage in here, but really came out of Player Stage, you know, the general concepts and the general energy about this back in around 97, 98, 99. And that eventually grew into people like Willow Garage really running really hard with this idea, grabbing a lot of people from the Player Stage community, eventually winning over all the people who'd written drivers and plugins and algorithms to joining the ROS community. That turned into a ton of economic successes, kind of below the fold there. And Willow Garage eventually turned into the Open Robotics Foundation, Open Source Robotics Foundation. And they had a ton of spin-offs like Fetch Robotics and Savioke, who were doing tons of amazing things with ROS 1 systems. And of course, early adopters on the right here were industrial partners, government partners, military partners, and that turned into, you know, kind of all sorts of people. Like Autonomous Stuff, I think, is a really interesting group who literally sells cars that come out ROS 1 capable. Even DJI has products that they've officially supported with ROS and products that hackers have hacked and supported with ROS, like their Ronin camera rigs. So a lot of crazy stuff happening in the ROS community and a lot of great prototyping. That's been awesome with this. So I think what's really cool about ROS 1 is, you know, most importantly were the design patterns. I think the design patterns are the biggest awesome takeaway about ROS. And I think this really informs the general approach to robotics, even though they made a lot of architectural mistakes in ROS 1. So I think the amazing best practices that we learned from ROS 1 were, hey, you should really test in simulation. Simulation should be something that almost anyone can do. It's not really gotten to a point that where everyone can do it, but it's getting pretty close. Modeling your robots, the kinematics. This was something, once again, that when I was early in my career and in robotics, we had to do from scratch. We had to literally derive every equation from first principles, and you literally would have a robot that crashed into a wall because you forgot that 180 degrees suddenly flips to negative 180 degrees, and your math totally broke at that discontinuity. That sucks. And then finally, then we can start talking about high-level software architecture like composability, starting with launch files, action-oriented systems. So we were talking earlier about message passing, service calls, which is kind of a RESTful behavior, but kind of wrapping that all together, turning it into actions. Actions are these long-lived things where it's kind of like, hey, go to the grocery store, come back with a pizza. You can describe that in the action framework, and that's a really amazing thing. So that's turned into composable modules where you can write domain-specific libraries. So that's kind of the first thing you should think about when you're working on a new project with ROS is, okay, what things are already in ROS, what things are not in ROS? Can I just wrap this plugin that's already out there in the build system and then just import it into my ROS thing? And then, so that's kind of take a domain-specific library, just wrap it in a catkin package, and you're off to the races. It builds. And then, and the best part about that is once you wrap something in catkin, it builds on every Linux distribution there is. Awesome. So then take those libraries, those domain-specific things, import them, add some topics, services, or actions, make it composable. Now I don't have to know the difference between the types of pointers and the types of references that are passed around. I can just look at the message files. And before you know it, we're talking about generic nodes, and we're using Unix design principles once again, and we're building robots like that. So I think one of the companies out there that wasn't that, I made this particular set of slides like a couple of years ago, but it's actually the folks who made Earl Robotics, who are now working on HROS over at Accutronics. I think they've really taken this Unix design principle, they've embedded it down to the hardware itself, and now the hardware you can just plug into each other, and it just negotiates conversations. So then finally, the best part about ROS1 was that you could move crazy fast on these best practices and these composable modules. If you're on a happy path, things just kind of fly together like Legos. And the only brick wall really is that not everything's necessarily optimized for your exact scenario. So the best part is that you can get a prototype crazy fast, way faster than you ever could have possibly done in any other system. But then if you want to do optimization, well, yeah, you got to optimize just as hard as you would have in any other world. So it's kind of the cool thing about ROS is it gets you to that prototype significantly faster. However, like every piece of software, there are bugs, there's mistakes in architecture, there's mistakes in understanding that lead to mistake in how you use the tools. So ROS has some major limitations. The limitations that we're starting to see getting solved today in ROS 2 are primarily security. That's about it that we're getting solved right now from OSRF, that is. So the big thing about ROS, well, actually, I mean, really, it's the last two things that are getting solved by OSRF. So that is, it's not safe on an open network. So this is a warning to all the newbies. Do not take a ROS robot and put it on the internet. Do not take a ROS robot and put it on a coffee shop Wi-Fi. We will find it. We'll tell you that it's broken. And we'll ask you to please take it off the internet. All right. Cool. Some other things that are not addressed by anyone out there really right now. There's kind of a new crop of companies, a lot like RosHub right now, who are trying to solve the rest of this stuff. So there's a huge race right now to solve a lot of the software architecture and software engineering questions. So those other things are like users, authentication, authorization. What about managing your robots after they leave your, imagine if you could actually solve that security challenge. Well, now you have an operations challenge. So that's kind of what we're not really addressing right now in this particular talk. But those problems are out there. So with that background in mind, what ROS1 is, mostly a message passing system that allows you to prototype really fast and very unsafely. And you can take ROS2, and the hope is that eventually ROS2 will get to the point that ROS1 was with at least safety and security in mind. And to point out, like every software transition, this is a long grind. I've been using ROS since 2008. Prior to that, I built something that was a lot like ROS. It wasn't as good. We didn't have any drivers. But what we're seeing today is that the transition from ROS1 to ROS2 has taken a long time, will take a long time, and it will be really great because that effort was put in. So what that means is, in the meantime, it's a bumpy road. The transition may not work for everyone right now. Some people, it's going to be stops and starts for a long time coming. And this transition's been going on since 2014. It was originally slated to be finished in 2020. I personally don't think we're going to land in 2020 with ROS2 fully removing ROS1. So here I am at RosHub, and we're trying to build scalable clouds that serve ROS users, and you can throw ROS anything, anywhere, on anything really fast and scale it up as big as you could possibly want to, right? So back in 2014, we said, ROS has this weird problem. There's this thing in here called the ROS core. And it actually doesn't really do much most of the time. So, when you first start out, you're mostly writing code that are these green nodes at the bottom. You write your nodes, and your nodes do most of the interesting work on your robot. And most of the time, 90% of those nodes, you didn't have to write. You just downloaded them and you ran them. So that's what's really cool about ROS. But what happens when failure strikes? In ROS1, the failures cascade. So that is to say that if you had a robot that required 3 computers, and so just to date myself a little bit, my first robots all had single core computers with on the order of 1 gig of RAM, sometimes less. And this was like, we thought these were big gaming machines with like maybe a 40 gig hard drive. So we required multiple computers to solve a hard vision problem, plus navigation, plus actuation, plus path planning. That was easily 2 or 3 to 4 computers. In the year 2016, even up to 2012, we were using a ton of computers. So what we frequently had, especially on mobile robots, what I worked on for an extended period there, were that you'd hit a bump, and literally we had problems like the pins touching the processor would disconnect from the vibration. What the heck do you do about that? So bam, ROS core just happened to be, well, the way we solved it was we rotated the computer. Instead of being this way and the pins bounce, we turned it this way and the pins don't bounce. Heuristics. So, so you either use a clever heuristic or you suffer the consequences, and there's a lot of consequences you can't always solve with a heuristic. So if that node goes down, that happens to, and so ROS has this thing called the ROS core. It coordinates all the communications between the ROS nodes. This is where all of your parameters are stored. They're actually stored only in memory on the ROS core in one single process. So one, you can only scale up to the amount of memory that a single process can have as far as your parameter sizes go. Two, the number of nodes that you have is actually limited by the amount of connections that that one computer can make, and Linux actually has limits on the number of IP connections you can have. And then two, you've got to you've got to actually go and hit that one machine with all of your queries. So only one computer can handle all queries from all nodes from who knows how many computers. And up to this point, the design's really good because you get this fan out capability. So the cool thing about ROS, if we take back a second here, is that the ROS core coordinates the communications. However, the communications go direct between the nodes. But without us, the programmer, having to think about it, or us, really where we're getting to is us, the integrator, having to think about. So when it goes between computers, we don't think about it. When it goes between the same computer, we don't think about it. When it goes between processes in a single-threaded program, we don't think about it. Only, as Lucas alluded to earlier, do we have to think about traffic when we're using nodelets, and we're mostly just thinking about where the nodelets should be placed rather than the traffic itself. And so once again, it just happens automatically in the most efficient way possible. We're literally talking about message passing on the nanosecond scale, without us having to even think about it. So when that coordination system goes down, when that ROS core goes down, suddenly no one in the network can find their neighbors, find their friends, even find the thing inside the same program or process they're in. That really sucks. That sucks a lot. So how do you solve that? And so, to point out a little bit more specifically, there's three major types of communications in ROS1. You got parameters, which are data that we store inside the ROS core that we want to be accessible to every program. The second type of data are topics, which are the connections between nodes, and then services. So topics are kind of real-time streams, where services are RESTful calls. So RESTful calls are made or broken as we need them. So the weird thing is that when this breaks, we immediately lose all access to all parameters. No one can update parameters. No one can read any parameters. You might have changed a parameter in your memory, and it will not be reflected in anyone else's programs whatsoever. You can announce a new topic, attempt to subscribe to a new topic, and none, even the computers that were working, you will not be able to make a connection to even those working computers. And then service calls will immediately start failing. The interesting thing is that topics will remain connected, and if you do a really special thing with service calls where you say keep the connection open, which most people don't actually do, then those will also break. But they could theoretically work through failure. So what's the solution to all this? Other than rotating the computer and trying to figure out every possible failure mode, which, I mean, there's a myriad of ways that software fails, right? Memory exhaustion, network traffic, timing issues, there's a whole list of things. You're never gonna solve every single one. There's a whole bunch of CS theory people I just made mad. Okay, so the only approach is literally stop the robot, hit your e-stop, or have an automated e-stop or a wireless e-stop, and go around to each computer. And if you want to be careful, you could actually just go and restart one computer, theoretically at least, and hope that they remake the connections. But, oh yeah, that's right, ROS core stored all data in memory. It's gone, it was ephemeral. Man, that's a bummer. We really could have actually rescued the system. The other interesting thing is, so that ends up meaning you literally have to reboot everything. You have to reboot it all. But wouldn't it be really cool if you could just write maybe 3,000 lines of code and fix all of this silliness? This bug has been here for 12 years. It's a single point of failure. It's the most classic failure in cloud software. So as a cloud engineer and as a roboticist, as I was looking at this for literally the last 12 years, I was like, man, this is such a bummer. So let's stop and think again. So what are the problems? The problems are, it's a single point of failure. What does this end up trickling down to? It means that when we are engineering a solution, which is what most of us care about, we want to solve a problem like dinging the bell at the right time. We don't really care about all these little silly things. We want to think about like, well, maybe the robot has 2 arms and 2 computers, and we can hot swap out connections somehow. Hot swap would be really cool, but we don't have it in ROS1. It would be awesome if like the other nodes could somehow detect that the ROS core went away and get into a special state and somehow reconnect, right? But we can't even detect the system fault. It wasn't designed into the libraries. And then because of all this stuff, it means that you can't really fan out as large as we do in typical cloud computing applications. Fan out only really works when you have like some redundant oracle of knowledge or thing in the that helps connect all these things as you're fanning out. And then once again, that really silly in-memory only data storage thing, that's really the showstopper, honestly. So what's the answer? Put your memory into a persistent data store, first off. Use a data store that scales, like a database. Rewrite ROS core in a way where you can deploy as many ROS cores as you want on as many machines. Decouple memory storage from the separation of concerns here. So decouple memory storage from service discovery. So what that ends up meaning is that you can start to achieve some interesting goals, like maybe you can fail over gracefully. Maybe you could scale horizontally twice with capitalization or lowercase, I don't know. Maybe you could solve network partitions. So one interesting thing here that I was pointing out here is that in this failure mode, these 2 nodes, if this was a topic connection, that would have stayed connected. If this were a service connection, it does fail. So this is called a network partition, where sometimes things can stay communicating and other times they may not stay communicating. And that's really bad because those 2 nodes, if that's the only connection they cared about, they'll actually just keep working. Meanwhile, the house is on fire around them. So, so if you could solve that network partition, that'd be pretty cool, right? And then finally, you know, especially, so I'm a maintainer on robot web tools. One of the problems that people frequently post about is that queries are slow when you talk to ROS API, which is this bridging layer to talk to the core. There's also performance issues at the core itself. So anyways, it's hard to query for information about what's running, where and when or why. So if you wanted to do something like have one node that depended on another node starting, it would churn up a lot of CPU cycles just trying to check for it. So because we're using a database, you can do that efficiently now. So just to be clear, there's a whole lot of non-goals with with Vapor Master. So the whole idea of Vapor Master is this misty thing in the cloud that you don't have to think about. So the non-goals here are, you know, we're not going to fix every security issue in ROS1. It's not going to suddenly make it safe on untrusted networks. That means you can't go over the internet just by adding Vapor to a system. Don't do that. Please don't use it like that. This does not replace ROS2 in any way, shape, or form. DDS is you know, significantly superior and just the link level security and the field level security and all these other things than at least ROS1. And there's also some other things out there like SROS who do a better approach to security than Vapor is presently capable of. And then the next thing is, you know, we're a cloud company, so we're actually thinking inside of trusted networks for the most part. Or we also occasionally think about deploying this to embedded systems. So once again, we think the networks, you know, literally you could put a network on a PCB, right? So that's a relatively trustworthy network for most people. So we're not thinking about traversing NATs, for instance. Not a goal here. So what's new? So what is new, and what do we think we solve, or at least can be solved by continuing the development of this tool? We think that that what's new is using MongoDB as a backend data store in a robotics application. There's actually been some usage of MongoDB in the ROS world, but no one thought to put it in the core for some reason. So what this ends up meaning is all of the key data about the ROS graph, and that's what people refer to the primary pieces of data that's stored in the core, the ROS graph data, that can now be placed in MongoDB. So that means your nodes, where they're located, what processes, what computer they're on, the topics, what IP address, what port, Same thing with services and parameters, the actual data about that you put in there. The other cool thing about putting this all this into a database is that right now we actually have a 16 megabyte limit that's enforced by MongoDB, but there's tons of ways to get around that, and you have virtually infinite storage on your parameters. And so the other thing being that just having infinite numbers of parameters is actually also really useful, especially if you want to run at ridiculously large scale. So what do we think this could potentially solve? Well, we think this solves assembly lines. If you had to do some sort of hot swap type of behavior, we think that this could apply to you. If you're in mobile robotics and you're not super optimized and you have a lot of computers in there, just like I did, you could actually put extra computers and possibly build in redundancy. And in cloud services, well, redundancy and scale is the primary goal of any cloud. So the whole point is we can have redundant data stores, and MongoDB allows us to scale up to all kinds of crazy scenarios as far as redundancy and replication goes, and worldwide tagging of data, all kind of gnarly stuff. And then that ends up meaning we can kind of spread the load of ROS cores. We could even deploy a ROS core per computer in a cloud environment. And that's actually what we do at RosHub. And then finally, we can deploy your application alongside that ROS core, and you can scale and replace or reconfigure things to your heart's content. And this is all possible because of the modular design of ROS, the Unix design philosophies that were applied, and that just happened to not get applied to the ROS core itself. So a little bit more in depth about how Vapor works. So in the simplest case, you actually need a minimum of 3 computers. There are some and this limitation is imposed by MongoDB itself. This is due to how the replication algorithms work. And this is just like some basic, and you start digging into that and you get into the basic computer science of databases, and that's a fun topic, but not everyone's interested in that. So the cool thing is MongoDB allows you to learn as much or as little about that, configure it as simply as you want. So in the true simplest case, you can actually get down to just 2 computers. And you have to learn a little bit about a MongoDB configuration flag. But the typical setup for us is a minimum, a quorum of 3 MongoDB instances with as many Vapor masters as we want, and our applications installed all alongside of it. So for instance, if you're in an embedded environment, you could literally just slap all of this in each embedded device. And we've run this on things like Raspberry Pis, and we've run this all the way up to things like Google Cloud Compute and inside of Amazon Web Services. So what about failure modes? So let's put it back through that same failure scenario: bumpy robot driving, bouncy CPU pins. So failure strikes. Oh no, it's shocking. That one computer totally went offline. Maybe it's a network partition. Maybe there's a momentary network outage. Maybe it totally rebooted. Who knows? But all of our remaining nodes, they actually know everything about the ROS graph still. The only thing that fails are connections to the failed node itself. The only thing that stops updating are the parameters that would have been updated by the other node, but those parameters are still there. And the best part is, because MongoDB is a very sophisticated database, we don't have this feature in here today just yet, but this will be coming out in later releases. We will actually be able to detect the failure immediately. So, well, how do we recover from failure? So if that node were just network partitioned out and our network connection suddenly came back somehow, well, the connections could just be reestablished. So we do need to add that new failure detection system. But if you have that failure detection system, we can add an action lib that would tell you could have essentially just a single library that you add to every program that says restart stuff, reestablish my connections for me. So we'll have to add another library down the road to do that failover. But once that's in place, it'll just pop right back in like nothing happened. And then because the parameters were stored in MongoDB and stored in a persistent fashion, if that node actually rebooted or crashed in a way where it lost all of its persistent data, if you were a good system architect, you could place all the right data into the persistent store that you need. And it's right there, right back for you. The only thing you have to concern yourself is optimizing around the speed of which you're updating your data and how that affects your system. So suddenly we're back to our use cases, our own design scenarios, and the ball's back into the app developer or integrator's court. So how large can it scale? That's a good question. The key takeaway here is that ROS is not the limit. It's no longer ROS. It's suddenly things like the Linux kernel. It's suddenly things like your network card, suddenly things like MongoDB and your ability to configure it. So you can scale out as much as you want horizontally with as many vapor masters. You can separate your vapor masters from your cores. So you could have a kind of a 3 classes of compute, for instance: database, ROS, ROS service discovery, and then finally nodes themselves. But does it work? So we open sourced this back in January. We gave it away for free as open source on GitHub. We wrote a blog post. We announced it on Discord, on ROS Discourse. And we actually got a shocking number of installs. We really thought like there's gonna be like 10 guys who were like, I like clouds. And we actually got hundreds of downloads overnight. So we actually discovered, we think there's a real pain point here. And the funny thing about all of this is only about 3,000 lines of code. So this could have been solved, very rapidly. So we actually solved this over a year and a half ago, and we thought it was so basic and simple because it was like 2,000 or 3,000 lines of code. We didn't even think that anyone needed it. We thought that we had just like some crazy special use case. And then finally somebody else looked over our shoulder and they said, holy crap, this is amazing. So anyways, so we released it. At the time we released it, we were just like, oh, it works for us. We didn't really think about how other people's scenarios worked yet. And so you'll notice this is actually, we were like, oh man, I wonder why all these people are uninstalling it, huh? But it works. I mean, it works for me, right? It works on my box. And then we took a step back and we said, well, let's ask some of the people, and bug reports started piling up. And we're like, huh, that's a weird bug. Oh man, that's an even weirder bug. Oh man, that's confusing. So then suddenly we realized, oh, there's this thing called ROS test. You can run a test pass against your rosmaster actually. Then we found some bugs in ROS test and in the rosmaster test cases. And then we discovered that, okay, after all that silliness, we could actually point it, we eventually figured out how to point it at our rosmaster, our vapor master that is. And suddenly the result was it failed. And we're like, oh man, that sucks because it worked for our scenario. And then finally we discovered that, okay, there's 15 tests, 12 of which were failures. So, coming soon. This is our test pass from this morning, actually. So it was a success, woo! This hasn't been, we're actually still in review right now. So hopefully we will PR this rather soon, and we'll hopefully make it all the way through. So anyway, so we got 0 errors right now and 0 failures. So kind of future work are things like, I mentioned this, I mentioned this in the slides here. It's in the Snap Store today. We discovered while we were trying to push this to the Deb storage that it was a multi-week process. Like back here in January, I think January 2nd, we said, oh, we got back from Christmas vacation. Let's just post this thing, and we posted it, and we waited, and we waited, and we waited, and then we said, huh. And then we noticed some work that Kyle was doing, and we said, huh, maybe we should just use this snap. And bam, like it was installed, it was working, it was great. And meanwhile, we waited and we waited and we waited. By the time our snap had lived and died, our deb package landed, right? What good does that do? And we can't tell that people were failing over here either. In the deb package world, we'd have no freaking clue. So really the Snap Store is the next big thing for ROS, because you can actually rapidly respond to your users. So that's future work. We have a lot of work that we want to integrate snaps further. We actually install the Vapor itself as a snap, and then that snap can be, so right now it can't be configured, you have to do it manually. But we want to make that nice and easy so you can do snap set, snap get. And then we got to write some tutorials because we kind of are the only people who know how it works. And then we need to kind of complete the API, which actually this is mostly completed with the next PR. And then some of the harder things are hot swap support, ROS leader election, and we want to do some other, we want to support some other auto start scenarios outside of the Snap world. But yeah, so that's basically where we are today. Any questions? Yeah. Yeah, 100% open source. I can't remember if we're BSD or MIT licensed, but one of those two. Oh, Apache, excuse me. Okay, that's pretty different. Oh, that's the beautiful thing about MongoDB. So, I mean, yeah, the MongoDB license kind of is annoying, but I mean, for us, a cloud company, we're just like, whatever. But for some people, we can understand that might be problematic. So we run it both we've tested it on embedded devices, so you can totally run it there. We've run it using MongoDB Atlas, so it just scales up there, and we just pull a slider that says go bigger. So that's, yeah. Cool. Well, with that, I should turn it over to Sergey, who's going to talk about wet lab automation.